Now we have demonstrated that these operators, A and A dagger, play the role of a ladder operator in up or down direction. A decreases the values of n by 1 unit, and A dagger increases those. So the next thing we will consider is the following. You start with this one. So it takes you to n plus 1, and then you act on it further. Okay, let me do it. Okay, let me use a schematic notation. So n, act on it by a dagger, you take it, it takes it up to n plus 1. Act on it further by another a dagger, it takes you n plus 2. And it goes on. And do it in the other direction. You act on it by a, takes you down to n minus 1. Another a takes you to minus n minus 2, and etc. So how do we make use of this ladder in making a prediction concerning the nature of n? The extraction is the following. If n is integer, or perhaps if with the opposite, if n is non-integer, what happens? What happens is that it decreases, and it really decreases all the way to minus infinity, and it goes through. If you start with positive non-integer, it decreases further. You leave the positive region, you go to the negative region, and so on. So the sequence of lowering will not terminate. I hope I convinced you, right? If it is non-integer, each time you decrease it by 1, you leave the positive region, go to the negative region, and you go all the way to minus infinity. Does this contradict something? Well, this leads to a contradiction. What is that contradiction? Contradiction. What is that contradiction now? That contradiction is following. Let me work out there is a bound on the values of n. What is it? And let me consider this expectation value. What is it? This is, well, there are two ways to determine this. One is that this is equal to, this is acting on here, gives you n times n, which is normalized, so it is equal to n to start with. I can also rewrite it in the following fashion: n, a dagger, a n, a n is the new vector that you obtain by acting a on the n, and a dagger n of it is its bra. So it is really the magnitude of this vector squared. It's the norm of that a n vector. So it is always positive definite, right? And it can be 0 if a kills the n, gives you 0. So what we get from here is that n is, from that beautiful and simple theorem, n is a non-negative thing. positive quantity. So if we start, in order not to violate that rule, we should not start with a non-integer. Because once you start with a non-integer, and if n can be non-integer, you violate that rule and go all the way to minus infinity. So, in order for the sequence to terminate, not to go beyond the positive values and hit the minus values and go all the way to minus infinity, we have to have n integers. As a matter of fact, positive integers. Well, here the argument is that it's integers. What is the minimum value then? If n is an integer, you start with an arbitrary n, you act on it by the a, you use that sequence, you go to n minus 1, a minus 2, etc. And lowest value should be 0, with n minimum being 0. So that's really very nice. Remember, E was h bar n plus a half. So what is the E minimum that you can get from here? It is a n minimum in here, which is 0, so h bar omega over 2. So the lowest energy that you can get is never 0, and it is that particular value. So that takes us to a very nice place. What is the corresponding state? Corresponding eigenstate. To this, or n equals 0, right? The h and capital N are two commuting operators. They have common set of eigenvectors. The corresponding eigenvalue for n equals 0 and E min is this. We denote that state by this expression, by this notation. That is, 0 means n equals 0. That's indeed the state. Okay. Question now. If we know this, can we construct the other states, like the state 1 and the state 2, the state 3, and all the way to n? Yes, indeed, we can. And we start with the 0 and act on it by the a dagger. What do we get? It should increase the eigenvalue by 1, so we should get the 1 in here. What about the normalization constant? Normalization constant will be the 0 plus 1, right? And whatever value there is, you add to it by 1. We have worked out those rules. And that's square root of 1 is 1, so there's nothing in here. So if we know the 0, we obtain the 1 quite easily. And that already tells you that you can go on all the way. So let's go on to the a dagger 1. So it's using that rule, it's going to be 1 plus 1, 2. That's square root of 2. What does this tell you? This gives you the following rule. 2 is obtained by this, which is, if you replace that with the original one, so 1 over square root of 2a dagger squared on 0. So that makes it more systematic, right? You start with the 0, 1 is obtained. Okay, let me write it in that systematic fashion right here. 1 is obtained by a dagger 0. 2 is obtained by acting on the 0 twice. There's a normalization compensation factor. And let me repeat it to 3. If you act on the 2 by the a dagger, it is going to be 2 plus 1, 3, that is square root of 3 and 3. So I solve for 3 and write it at 1 over 3 a dagger on 2, or if you read a dagger on 2 from here, it is 1 over 3 to a dagger cube 0. So that already gives us the systematic, right? This is 1 over square root of 3. This is 1 over square root of 3 times 2. Then obviously there was here a 1. So if you go generalize this, what do you get? Here, perhaps I have to write underneath. N will be obtained by n factorial. At each level, it's 1 over 2 times 1, 3 times 2 times 1. If you go to the next 4 times 3 times 2 times 1, 1 over n factorial for the normalization, a dagger to the n and 0. Okay, that's the result we obtain from there. So this technique is quite useful in the following sense. If you can construct the 0, the minimum energy state for the oscillator, then as you know what a dagger is, by acting on it in the number of times required, then you get the excited states. Number of times you require, that is, if it is 2, you have to act it twice. 3, if it is 3, 3 times, or 27, you have to act 27 times. So it's a very nice recipe, really. So I will turn my attention to actual construction of it, but before that, there is a nice consequence of this, is the matrix elements of A and A dagger in the n bases. Now I can use n as a basis, right? Because they are integers, they are real, and they are the eigenvalues of Hermitian operator, thus they are orthonormal and complete. So they have all the nice features that you look for in a basis. Complete and orthonormal. So what is the matrix representation of A and A dagger in that basis? So you just consider the following: n prime A and n. An is what? Square root of n. So this is then square root of n prime, n minus, sorry, I'm very sorry, n minus 1, of course. N minus 1, that is, then you read it as, I hope it is visible in here, n prime n minus 1. And similarly, a dagger, n prime, a dagger, n is square root of n plus 1 times n plus 1, n plus 1, n prime n plus 1, which is n plus 1 delta n prime n plus 1. Well, these are rather skewed, really, exotic matrices. One thing which is clear, they are off diagonal. They are not diagonal. Is it normal? Yes, of course. Because n are not eigenvectors of the A or A dagger, because capital N and A dagger do not commute. Therefore, you wouldn't be expecting to get diagonal anyway. So this is not something which is disturbing. This is something which is comforting, which verifies your knowledge that if they are not eigenvectors of the A and A dagger, the matrices naturally do not turn out to be diagonal. What is the form of these matrices then? For instance, what is the A? Well, let me try to show you a little bit. This is the diagonal position, right? Etc. It goes on like that. If this portion is m prime, And if that portion is n, when, for example, n prime is 0, and 0, 0 is 0, 1, 1 is 0, 2, 2 is 0, 3, 3 is 0. If it is 0, this one is n minus 1, so you have to start with 1. If it is 1, no, 0, it's, n is, to get 0, it must be 1. Perhaps I have to use the color to denote, okay. So that's this parallel to the diagonal lines, which is above the diagonal, is the matrix representation of A, because to match the first index, it must be reduced by 1 unit, okay? So n must be 1 unit up so that it matches to the left unit by decreasing. And if you look at the A-dagger matrix, in the A-dagger matrix, perhaps I can use the red color in order not to plot it twice. Now if I take the A-dagger, it's going to be in here. The purple one is the A, and the red one is the A-dagger matrix element, not along the diagonal, but just parallel to the diagonal in both directions. So these are the matrix representations of the N and A-dagger in the N representation, and we may also wish to have the matrix representation of the physically relevant Hermitian operators, X and P. We will need that most often. And based on those, we can work it out. If you solve for, remember we have defined A and A-dagger in terms of X and P. That's a constant times X plus I P over M omega. And the other one was the conjugate. If you solve for those in terms of the X and P, you get the following. X is H bar divided by 2 M omega, A and A-dagger. That's the X. Now notice that despite the fact that A and A-dagger are not Hermitian, X is Hermitian now, because when you take the Hermitian conjugate, this goes to A-dagger and that goes to A, therefore it's Hermitian nicely. And if you solve for P, the same expression, you get the following. At first you may feel a bit disturbed saying, well, let me write this first. If I hide this, you say because of that combination P, is there any danger of being non-Hermitian? Of course not. This goes to minus A-dagger. This is A, and there's an overall minus, but there's an I in here. Everything is so well tuned. Well, you started with the Hermitian X and P to get the A and A-dagger. When you convert them, of course, you were expecting to get the Hermitian things, and you do. So what are the matrix representations now? That was easy, but it involves two terms. Let's do that. What is the, for instance, n prime x and p? It is this factor. Let's leave it there. N prime a n and n prime a dagger n. This one is n delta n prime n minus 1. This one is n plus 1 delta n prime n plus 1. And that's it. So what do you expect? You will work it out, of course, accordingly. And if you think of the matrix again, if I can do it properly, on the board it's always difficult to do it. Notice that each term are off diagonal. So there are zeros on the diagonal positions. It's going like that. There are one class of terms coming from the A part, purple. Yeah, there I was using. This is from the A part, the first term, and there's also a red part. Anyway, it's also off diagonal, and there are two sets of terms only. One is just to the right and to the left, there are two off diagonal lines. That is X. P is similar. I'm not going to work it out because it's the same type of idea. When you know the A and A dagger matrix elements, and you just substitute them there. Question, X and P. They are Hermitian nice operators. They didn't turn out to be, I'm joking, of course, this is too trivial as a question. They didn't turn out to be diagonal either. Is this a problem? Obviously not, because X and P do not commute with the Hamiltonian, neither with the N, right? Therefore, it's only natural if they do not commute with those N operator, why it should share the same eigenvectors or have the diagonal form in the representation. It's not diagonal. That's also natural, and it verifies our existing knowledge that only the commuting operators have common set of eigenvectors in which both of them can be represented diagonally. So that is nice. The next thing I turn my attention is how to construct the zero, because that discussion taught us the lesson that if I know the zero, I know everything essentially, right? So let's try to solve the zero, the minimum energy state, which we call the ground state. Minimum energy is h bar omega over 2, and the corresponding state is what we have denoted by 0. So how to construct that state? That I may need. Let me leave it here. Okay. Okay, that's the title of this subsection. We are going to construct the zero ground state. How do we define the ground state? A acting on it gives you 0. Kills it so that you cannot go beyond, because that's still the lower limit of the eigenvalue n, little n. If so, if I project this on the eigenvector of the position operator, that's again 0. Well, obviously, as I am sandwiching this or projecting this on an eigenvector of the position operator, I need to work out the explicit expressions of the A in terms of the X operator and P operator, which is m omega 2h bar. Now I use the capital letters. Remember, when there is I told you, when there is a danger of confusion of the eigenvectors and operators, I resort to capital letters for the operators. X operator plus I over m omega P operator, right? That's the definition of the A in terms of the X and P. Oh, that's nice. So if I take this out, that's a number. The right-hand side is 0, so I don't need that number. Then how do I proceed? X operator plus I over m omega P operator, 0 equals 0. X and P are Hermitian operators, act on right and left the same way. What is the action of this operator to the left? It is X times X. That's the definition of eigenvalue equation. What is the action of this to the left? Is it? We need to be careful. I wrote this incorrect expression on purpose to draw your attention, because signs are important. So let's remember. We have, remember, we have introduced the P operator as the generator of translation. And that was the way that we could work out the signs and everything correctly. So it's not correct. What is the correct thing? P acting on X. On the cat, it's more comfortable to work. P acting on right. This sign is correct now. Remember, I told you and warned you several times that P, when acting on the wave functions, which are the coordinates in the spaces, it would be minus I h bar d by dx, or h bar over I. But when it's acting on the basis vectors, it was acting this way, oppositely, because we were constructing the generator of translations on the basis vectors. So if it is so, how does it act on the explicitly when I go from here to there? X, as I cannot turn the P around, put the arrow saying that it's acting to the left. When you are converting this, then it becomes minus, right? This is a very funny way of writing, but let me write it again. So that was a wrong sign. Let me correct this now. I have done this exercise, perhaps some of you may say unnecessarily, but please do it. It was a important point, a point where everyone can get confused easily. So what do I have then? If it is minus and there is an I squared, that is a plus now. Otherwise you would get a wrong sign, minus sign. So what do I get in there? Then, as this is a minus, there is an I squared, there is then another minus sign, plus. So the equation is this: x plus h bar over m omega d by dx on 0. But this derivative is acting to the left, right? Because it is the only place there is a dependence on the position vector. So if I take it out, well, this is 0. If I take it out, x h bar m omega d by dx. Now this is more, in notation-wise, more consistent, because this derivative was acting to the left anyway, so I freely pulled it out. And I have this expression. What is this expression? Well, this expression is the wave function associated with the ground state. Actually, it is really psi 0 of x. What do I mean? You expand that state in terms of the position eigenvector basis, and the coefficient will be the psi 0 of x. Can I solve this? Yes, we can solve that equation. Now, it's a simple differential equation. And the book introduces a notation. Let me repeat the notation. And he calls this h bar over m omega. He calls it x0 squared. Defines it this way. And the meaning, actual meaning of it may be clear when you go to the correspondence limit, and you can associate this with the amplitude of the oscillation at the classical level. That's the meaning that you attribute to h bar m omega. But let me use this as a notation, because it involves the constants of the problem. The mass is the mass of the spring, and omega is the related to the spring constant k, and h bar is the Coulomb constant. So it is a constant. So how do I solve this equation? Well, this equation can be solved in the following manner now. D by dx, x and 0. Well, let me use this, my simpler notation, and then we can go back. The book keeps using this, equals x and 0. But this is, I guess, not a bad notation, which would make us feel comfortable. So when this factor goes to the other side, minus 1 over x0 squared, and x and psi 0 x. That's a really nice, simple equation. How do you solve it? You solve it in the following manner. This is psi 0 divided by psi 0, 1 over x0 squared, x and dx. You change these to a generic variable and integrate indefinite integral. Change it to this. and integrate from 0 to x, for instance. This 0 to x. This is 1/2 x to x squared. And you define the value associated with the left-hand side at the origin as a constant. So what is this? The integral, the logarithm, right? Logarithm of psi 0 of x minus logarithm of phi 0 at 0, and call it a constant minus a constant log c. Then you have psi 0 of x, a constant times e to the normalization constant minus 1/2 x squared divided by x0 squared. Okay, let me write it as such. Will be determined by a normalization. Nice, isn't it? In the book's notation, this is x0. So ground state wave function comes out to be a Gaussian. That is really one of those features what makes this harmonic oscillator a beautiful example, beautiful working ground. It has a Gaussian distribution. And what are the other things? Perhaps you are familiar with the solution from your previous quantum mechanics courses or modern physics via the Schrödinger equation. Eventually we will discuss that. In the Schrödinger equation, what you do is you have a wave equation in terms of the wave functions. That's the coordinates. Potential is given, and then you solve a second-degree differential equation. In this case, not partial, it's straight because it's simple, one-dimensional. And you get that the solution will be a Gaussian times Hermite polynomials, finite degree things. And we are getting it through this operator method beautifully. You see, it is the ground state. Once that is understood, then you will act that operator on it, and it will give you the desired solution at any order you like. And let me demonstrate how do we proceed once we know that. The first thing, of course, that we had to tackle with is to determine that constant. Well, to determine that constant, what you do is you write this as n, for instance, n, and you take dx minus infinity to plus infinity psi 0 x squared. You set it equal to 1, and then the left-hand side becomes n squared. You can take, of course, mod squared, or you take it up to phase a real number. Dx, the square of that, so it gives you x squared divided by x0 squared, because when you take the square of this, there's a factor of 2 canceling that 2. And the integral again from minus infinity to plus infinity should be equal to 1. I already, I guess, told you in the past how to determine this Gaussian integral and convert it to the following: dx e to the alpha x squared minus infinity plus infinity. That's the prototype. That's the generic integral that you have to remember. That's pi over alpha when you write it in that fashion. And the demonstration is easy. I think I have tried it once. I don't know whether it's in class or you have to know how to carry out these integrals like that, really, instead of looking at the tables. You call it I and take the square. When you take the square, of course, you have to introduce different dummy variables, x and y. And there is the measure becomes dx and dy. The exponential becomes e to the minus alpha times x squared plus y squared. Go to the plane and go from xy to r theta. And you carry out the integral, take the square, you get the square as pi over alpha, take the square root, you get the square root of pi over alpha. It is so important, and it's the basis of at the heart of the path integral formulation of quantum theory. So this Gaussian integral should be known by all, I guess, like that, really. Well, I summarized the demonstration in half a minute. Actually doing it takes 2 minutes, say. Summary takes half a minute. Therefore, so I now try to proceed a little bit. I have been able to work out the constant. So this alpha is 1 over x0 squared. So what do I have? N squared times pi over alpha. Alpha is 1 over x0 squared. So x0 squared. is 1. So n is 1 over pi to the 1 over 4 x0. So that's the normalization constant. You see, it's not really too difficult when you have a Gaussian to have a normalized Gaussian. So psi 0 x then is, psi 0 x is 1 over pi 1 over 4. Yeah. Yes, thank you. E to the minus x0 squared, twice x0 squared. So that's your ground state. Nice. So what we do next is, what is x1? Psi 1 of x, that is. Which is x, a dagger, and 0, right? That's the expression. So this one is, carrying it over, m omega over 2h bar times x plus minus. Now that was I minus I p over m omega on 0 and here on x. So I need to solve this. Indeed, one was obtained by acting on 0 by the a dagger. I projected on x to get the wave function, right? Psi 1, so-called psi 1 of x. So, okay, let me proceed here, and then I will move to the left corner. M omega over 2h bar x and xn minus I p over m omega 0. Again now, using this correctly, p acting to the left is minus ih bar. There is an I in the front, makes it plus, but there are no overall minus, so this minus is important. So you get the following. X minus x0 squared d by dx on x0. How nice. These signs are utterly important, so I invite you to really pay attention when you are doing it on your own. So what do I have then is psi 1 x1, which in my notation I indicated as psi 1 of x, m omega over 2h bar, x0 squared d by dx psi 0 of x. That's the algebraic method, really. Once you obtain the psi 0 of x, then you act on it by that algebraic operator, and you go all the way up. So you will need this expression. Well, let me call it the n0 eventually, because I don't want to get confused with that. Okay. So n0 times this factor times x and x0 squared dy dx e to the minus 1/2 x minus x0 squared. So what is this? This factor perhaps should be handled. This one is called 1 over x0 squared. So perhaps that's all it counts in here. 1 over 2 x0. 1 over 2 x0. I could have left here and call it x0 squared, but let's leave it out. Now, how about the x on 2? I would like to not really finish it. I would like to give it in the compact form. X on 2 is x. 2 is a dagger over square root of 2, 1. We worked it out. To get the 2, you act on the 1 by a dagger, but there is this normalization constant thing. So then it is 1 over square root of 2 x a dagger is, again, that factor, m omega over 2 h bar x on I p a minus m omega times 1. Times 1 is, okay, x1. Really? So, writing it as x minus x0 squared d by dx, and writing this as 1 over, again, 2x0, then you get the following. One over 2 x0, x minus x0 squared, you are moving this out, d by dx, x and 1. Right, that's it. x1 is this. x1 I copy from here, and 0, 1 over square root of 2 x0, x minus x0 squared, d by dx, e to the minus 1 over 2 x divided by x0 squared. So altogether, let me put everything here. One over 2. 1 over 2x0 combines squared, x minus x0 squared d by dx squared, because this factor there and that factor, the same factor, times psi 0 of x. We will generalize this using the recursion argument. Look at here. The factor is one of this once only, and one factor, and then 0 for psi 0. This is acting twice, and that factor squared. There's an additional factor of 1 over 2. When we go to the 3, there will be an additional factor of 1 over square root of 3. So I can now write the results before giving the second break. So we have seen the systematic, and the final result that we obtain is the following. Psi n of x, which was x on n, is equal to 1 over n factorial, this additional one. As I said, if we go to the 3, I would have an additional 1 over square root of 3 coming from that. So that's 1 over n factorial times 1 over square root of 2x0 to the nth power. Again, we have seen that systematic here, right? There was once of this factor from the 1. There was square of this factor from the 2. If we were going to the 3, there would be cube. If going to the n, it would be this factor. Nicely. And nth power of this operator times psi 0 of x, which is 1 over pi to the 1 over 4 and x0 and e to the minus 1 over 2 x0 squared. And finally, what is x0? H bar over m omega. So that's our final result. We have been able to construct in an algebraic and closed form of the nth eigenvalue of the harmonic oscillator. So you can really carry out this algebra. And it will give you the Gaussian will survive, and the rest will give you the Hermite polynomials, which you can obtain alternatively in the context of Schrödinger theory. So it's again a nice point that we should give a break, and we'll continue after the break.